All right, welcome again to what I hope are good choices. It's hard to know until you've already made them, and then sometimes it feels like it's Schrodinger's choice, where if you had done the opposite, it would have been just as bad, if not worse. So I'm trying not to do that. I think the LPIC makes sense. I've discovered that, or sorry, I've discussed that in a lot of other videos. There's at this point in IT, I made a video about this too. I feel like there's just a lot of different certification tracks you can go down, and I feel like this is kind of, and I've talked about this in other videos. I feel like that's kind of anomalous. Like it used to be less the case that you could learn like if you just think of cloud. There's at least three major cloud providers. There's AWS, GCP, Azure, but there's also cloud that you don't really think about. There's like the Cisco cloud, like Vipella. Like there's a whole, which I'm surprised, it's not even listed here. It looks like, and then there's like Juniper cloud certifications as well. There's a whole track for Juniper Cloud. So it's like, yeah, I've talked about this in other videos, but let's keep going with this. I've got a lot to celebrate because this is the oh, actually, never mind. So I'm actually almost 3/4 of the way done. So let's keep on going. We're talking about GNU and Unix commands. The objective for this lesson 1 of 103.4, is to use streams, pipes, and redirects. And there's going to be 2 lessons in this. All right, so introduction. All computer programs follow the same general principle. Data received from some source is transformed to generate an intelligible outcome. In Linux shell context, the data source can be a local file, a remote file, a device like a keyboard, etc. So this is the data source, how you send data to the system. You can send it via a file on the system, a file on another system that is accessed remotely by the system, or just basic, manual inputs by a person, like through a keyboard, mouse, VR headset, whatever. So the program's output is usually rendered on a screen. So that's output. Input is through all these methods. Output, usually it's via a screen. But also common is to store the output data in a local file system, send it to a remote device, and play it through audio speakers, etc. And we can think of some more different kinds of computer output. Might be kind of hard because I think there's once you're talking about screens, I think screens and speakers, that's kind of the main kinds of output. I guess the other thing I could think of when it comes to output is like a storage drive. Like if you burn it to a CD, or like you save it to a thumb drive, like that would be output, is like storage that you're producing. But I think screens and speakers are the main ones. All right, so operating systems inspired by Unix, like Linux, offer a great variety of input/output methods. In particular, the method of file descriptors allows to dynamically associate integer numbers with data channels so that a process can reference them as its input/output data streams. So this is file descriptors. It's an input-output method, and it can dynamically associate integer numbers with data channels. Standard Linux processes have 3 communication channels open by default. The standard input channel, most times simply called STDIN, the standard output channel STD OUT, and the standard error channel STDERR. The numerical file descriptors assigned to these channels are 0 to STDIN, 1 to STDOUT, and 2 to STDERR. Communication channels are also accessible through the special devices. So /dev/ oh, I didn't know this, STDIN /dev/ STDOUT and /dev/ STDERR. All right, I didn't know that. So let me actually look at that, because that's interesting, and that could be useful for like scripts and stuff as well, because like you could access the input and the output just by looking at those files, or like whatever those are. So let's go to let's use the file command on STDIN. All right, so it's a symbolic link. Let's take a look at what it is for STDOUT, symbolic link, and ERR, symbolic link. And you can see that they correspond to 0, 1, and 2, like it said in the documentation. So we have. Let's just go right with this symbolic link. Let's do a file on the actual link itself, or the actual the thing that the symbolic link is pointing to. Oh, this is interesting, and it's another symbolic link. That's interesting. All right, so looks like we found it. This is a special character. So I don't know what that means. Can I cat it? I can't really cat it. Oh, you know what? I can cat it. And what it does is it just reprints what I had it. So this is the STD in. So it's just printing what I typed in. It's returning the input that I give it. So let's take a look at what happens if I cat out the STD out. So it looks like I don't get anything, although that might not be the same final location. I'll have to use the file command to determine if it's different. Oh, this is interesting. So it actually looks like it points to the same thing. I wonder if that's also the case for STDERR. Oh, I gotta spell file correctly. Yeah, so they all point to the same location. This character special file type. So that's interesting. Yeah, it just prints out whatever you put in there. Let me try one more thing. We're gonna cat this out, and then we're gonna go open a new connection to my lab, and then what we're gonna do is type echo hello world. Okay, that's interesting. So nothing showed up here. I was wondering if that would be the case, but maybe because it's a different terminal section. One thing people who have followed this channel might be aware of is there's a file on Juniper devices called interactive commands, where you can just run that file and you can see. Oh, and I have to start the. I have to start it. Shoot. Okay, let me start it. Okay. Yeah. So, GNS3 server. There we go. So, yeah. So there's a file that kind of works the way I thought this would work. Oh, and I changed it to 100, so let me change that over quick. No, I do not want that update. That would ruin everything. There we go. Apply. Okay. It's 105 degrees outside. And I wonder why I don't want to go outside today. That's why. Okay, here's all my projects. So, is there like maybe this temp project? Let me open that and see what that was all about. Yeah, okay, here, perfect. There's a Juniper device. So we'll open up the control plane after we start it. Yes, start all devices. Things will boot up pretty fast. That's kind of the power of this lab. Unless, of course, it's broken, which is always a possibility. Anyone in tech will know that. Okay. Yep. Something happened, it looks like. Huh. Interesting. Oh, it could not load the IOU license in the preferences dialog. Or maybe let's hit this again and see if now, you know what, now that I have it running, let me open it again. It might behave a bit better. Okay, and then I'll open the temp. There we go. So now everything is running. Okay, and now we can look at, you can see it's already at the wake up daemon. If you're just running this on your own hardware, not on a server like I have, you know, it takes a while just to get to that part. And then the unblocking device takes even longer. So home lag is still pretty solid. Probably use an upgrade at some point. It's older. It'd be nice to get more CPU. But setting it up is a ordeal. So to save that would be nice. Okay, so while this is going up, and you know what, this is kind of irrelevant anyway. So I just wanted to explore these files. We did that. We saw that they all point to the same location ultimately, which is this 0. These are all symlinks to a location, a path. Yeah, the other thing we noticed is that when you open a new session, it doesn't take the input from that session and display it in the file. It's only the input you give in the session that is open, which is unfortunate because I thought it'd be different than that. There might be something in like var logs, like I'm really curious if this has it, because it's a wonderful feature of Juniper devices, and Juniper devices are based off of Linux, so like probably would have the same things, right? Is there no messages? I'm kind of confused here. Here's the journal files that we kind of looked at before. Oh, it's a directory. And I remember there was like a utility to look at the journal files. Like you don't have to use cat. Yeah, and there it's like journal CTL. Yeah, and then you plug in the so like you can look at a system journal, you can look at a specific journal. Let's look at a system journal. Okay, so yeah, here's the boot up messages. Now I wonder, what I'm trying to look for is like commands. So can I do like pipe hello? Because I entered in hello world. Oh, pipe grep, I mean. There we go. Does this work if I do it like that? Okay. Well, let's search for CPUs just to make sure that this works as a concept. Instead, I search for cups. That does not show up. Yeah. Okay. So you can grep things out like that, and it looks like this is not, in fact, the way to look at. Oh man, this is frustrating. And I'm on a tangent. Apologize for that. I need to stop being on this tangent. But I'm genuinely curious if you can do the same thing here that you can do on Juniper. And what that is watch all the users on your system enter commands into the system. Like you can just run this command, sit there and watch what everyone's doing. I mean, that's absolutely essential when it comes to like making automated scripts, because you want to see like what your script is actually doing and like where it goes wrong and stuff. So like if this command exists, like that would be awesome. So you know what, let's ask the AI. That's a good way to move on from this tangent. In Juniper Junos devices, there exists a file called interactive commands that you can look at to see all of the commands being entered on the Juniper system. Does a certain mechanism like this also exist on regular Linux devices? For example, a Ubuntu device?
In Juniper Junos devices, you're referring to the interactive commands file, which logs commands entered in the CLI. In Linux systems, including Ubuntu, there isn't an exact equivalent by default. However, there are several mechanisms and tools that can be used to monitor and log shell activity. Bash history. The most basic form of command logging in Linux is the bash history, which is stored in tilde. Bash_history for each user. This file contains a list of the most recent commands entered by the user. However, it's not real-time, and commands are only written to this file when the user exits the shell.
Right.
It's also user-specific and can be easily modified or cleared by the user.
Yep.
AuditTD. The Linux audit daemon, AuditTD, is a framework to help you to monitor and audit system activities.
There we go.
With AuditTD, you can define rules to log specific system calls, including the execute system call, which is invoked when new processes start. This can be used to log all commands executed on the system.
Oh, that's good.
ACCT. The ACCT package provides tools for monitoring user activity. Once installed and activated, it logs all executed commands system-wide in binary format. You can use tools like last count to view the log commands. PAM. The pluggable authentication module's PAM system can be configured to log shell activity. By using the PAM_TTY_audit module, you can enable or disable the auditing of TTY input for specific users or groups. Third-party tools. There are third-party tools like Snoopy and PSACCT that can be installed to log commands executed on a system. If you're considering implementing any of these for security or auditing purposes, remember that a determined attacker with root access can potentially bypass or modify these logs. It's essential to forward logs to a remote, secure logging server and to regularly monitor and review the logs.
Yeah, so like if you're gonna do scripting, even like using Ansible, something like that, it's absolutely essential that you have something like this in there, because you want to see like what was actually done. At least in my opinion, that's just my opinion. But it looks like, unfortunately, the built-in way, like the intended way for that to occur, is looking at the bash RC. I mean, I feel like a lot of this early development didn't have, the modern way of using computers where like everything's in the cloud. And so like the fact that this tool is missing kind of makes sense, because it's just a server, meant to be used by a few people. Where like a networking device like is designed to be accessed remotely more. But I don't know, I could just be making that up. So yeah, it looks like we do have some options to do that, but we'd have to install a third-party tool. Let's try Snoopy. We'll have to do this. Okay, so we've got Snoopy. Can relatively work. It is if it is mandatorily preloaded. This can do harm to your system. You know what? Let's try another one. Oh, is it installing it anyway? I thought it would cancel the install. Okay, I don't see it on there, so I think it didn't install. You know what? This is not a good tangent. It'd be nice to know how to do this, but I can figure it out when I actually need to know it. All right, so these three standard communication channels allow programmers to write code that reads and writes data without worrying about the kind of media it's coming from or going to. For example, if a program needs a set of data as its input, it can just ask for data from the standard input, and whatever is being used as the standard input will provide that data. Likewise, the simplest method a program can use to display its output is to write it in the standard output. A standard shell session, the keyboard, is defined as the standard in, stdin, and the monitor screen is defined as the standard out and standard error. The bash shell has the ability to reassign the communication channels when loading a program. It allows, for example, to override the screen as the standard output and use a file in the local file system as standard out. All right, next section is redirects. I need a break. I'll be right back. All right, I'm back and ready to go. I really can't do much more than an hour, so I gotta make sure I'm on topic. So next section is redirects. The assignment of a channel's file descriptor in the shell environment is called a redirect. A redirect is defined by a special character within the command line. For example, to redirect the standard output of a process to a file, the greater than symbol is positioned at the end of the command and followed by the path to the file that will receive the redirected output. I thought we went over that before, but here it is again. Now, from what I understand, you can have a space here. It looks like either is valid. I usually do it with a space, but here they do not have a space. By default, only the content coming to standard out is redirected. That happens because the numerical value of the file descriptor should be specified just before the greater than symbol, and when not specified, bash redirects the standard output. Therefore, using greater than is equivalent to use 1, 1 standing for standard output, 0 standing for standard input, and 2 standing for standard error. 1 is the value of standard out's file descriptor. To capture the content of standard error, the redirect to greater than should be used instead. Most command line programs send debug information and error messages to the standard error channel. It is possible, for example, to capture the error message triggered by an attempt to read a non-existent file. Okay, so let's follow along with the example here on my nifty home lab. So cat proc CPU info. Now 2 for standard error, and then I'll try it without the space, and then I'll try it again with the space. Okay, so there we go. Now let's try to cat out tmp error.txt, and we've got no such file or directory, which is kind of interesting because we did it here. So like why didn't that show up? So to capture the content of standard error, the redirect to should be used instead. Most command line programs send debug information and error messages to the standard error channel. It is possible, for example, to capture the error message triggered by an attempt to read a non-existent file. Okay, so, but the thing is, like, wait a minute. Oh, you know what? Oh, okay. I'm confused. So, no such file or directory. Oh, so here's the non-existent file here, this cat file. Oh, okay. So I'm confused here. See, what I thought is that I tried to cat out the contents of this error.txt, and it was telling me that the error.txt file didn't exist, which I'm like, what? I created it here. That makes no sense. Well, that's because I misinterpreted what's written here. So what we tried to do is we tried to cat out this file here, which does not exist. And then we can't do that, so we got a this message here. But instead of displaying it in the standard out, we redirected this standard error message into this file, and then we catted out the file which contains this. So I was confused as to what was happening here, but that is no longer the case. All right, so moving on. Both standard out and standard error are redirected to the same target with ampersand or ampersand greater than ampersand. It's important not to place any spaces beside the ampersand. Otherwise, Bash will take it as the instruction to run the process in background and not perform the redirect. Okay, that's good to know. Maybe I should stop using spaces when I do this. The target must be a path to a writable file like /temp/cpu.txt or a writable file descriptor. A file descriptor target is represented by an ampersand followed by the file descriptor's numerical value. For example, the 1 standing for standard out, greater than ampersand 2 standing for standard error, redirects standard out to standard error. To do the opposite, standard error to standard out, then you just swap the numbers, so 2 greater than ampersand 1 should be used instead. Although not very useful, given that there is a shorter way to do the same task, it is possible to redirect standard error to standard out and then redirect it to a file. For example, a redirect to write both standard error and standard out to a file named log.txt can be written as greater than log.txt and then 2 greater than ampersand 1. So what we're doing is we're redirecting both the standard error and the standard out to this file, which is interesting because, yeah, that's interesting. However, the main reason for I'm going to try that actually. That kind of isn't sitting well with me, so I'm going to try it again. So what we're going to do is we're going to cat out this file again that doesn't exist. So we'll get this standard out, which is what's displayed here, and then we'll get the standard error, which will be the same as what's here. So let's get both of them. We're going to do this, and then we'll do greater than log.txt with no spaces, and then a space, 2 greater than ampersand 1. Alright, now let's see what we've got in log.txt. Alright, so we've just got 1 line. I was expecting there to be 2 lines in there because, oh, you know what? I feel like this is not, correct, because I feel like you would have to, oh, okay. That's interesting. Huh, okay. Well, that's interesting. Alright, so however, the main reason for redirecting standard error to standard out is to allow parsing of debug and error messages. It is possible to redirect the standard output of a program to the standard input of another program, but it is not possible to directly redirect the standard error to the standard input of another program. Thus, programs Messages sent to standard error first need to be redirected to standard out in order to be read by another person's standard in. To just discard the output of a command, its content can be redirected to the special file /dev/null. For example, greater than log.txt to greater than /dev/null saves the contents of standard out in the file log.txt and discards the standard error. The file /dev/null is writable by any user, but no data can be recovered from it as it is not stored anywhere. An error message is presented if the specified target is not writable, if the path points to a directory or a read-only file, and no modification to the target is made. However, an output redirect overwrites an existing writable target without any confirmation. Files are overwritten by output redirects unless bash option no clobber is enabled, which can be done for the current session with the command set-o no clobber or set-C. All right, so let's try that. Set, and we'll do a help on set first. So the syntax is to give it options and then arguments. So -o is to set the variable corresponding to an option name. So the option name is -c. So there we go, no clobber. So set-o no clobber. All right, and then cat proc CPU info to there's tmp error.txt, and there we go. We don't have the clobber message, so we can't just blow away that file. Instead, we'll get an error. To unset the no clobber option for the current session, run set +o no clobber or set +C. To make the no clobber option persistent, it must be included in the user's bash profile or in the system-wide profile. Even with the no clobber option enabled, it is possible to append redirected data to existing content. This is accomplished with a redirection written into two greater than symbols right here. Right. So this is to append, right? Yep. All right, so let's unset that. So it's just the same command up there, set, but it's a +o no clobber. All right, and then we'll do the same command, and there we go. It overwrote the existing file because it clobbered it. Okay, so now we want to enable that again. There we go. Perfect. And then, okay, and then the next part. All right, so we've got the, okay, yeah, now we're appending, so we don't need to worry about whether it's clobbering or not because it's appending. If I were to do it so that it's not appending, then I get that no clobber feature in there. So now let's cat it out. I should have it 3 times, I think, because I did it an extra time. Yep. In the previous example, the new error message was appended to the existing one in the file /temp/error.txt. If the file does not exist yet, it will be created with the new data. The data source of the standard input of a process can be reassigned as well. The less than symbol is used to redirect the content of a file to the standard input of a process. In this case, the data flows from right to left. The reassigned descriptor is assumed to be 0 at the left of the less than symbol, and the data source, a path to the file, must be at the right of the less than symbol. The command unique UNIQ, like most command line utilities for processing text, accepts data sent to standard in by default. Alright, so let's take a look at the unique command. We'll do a help on that. UNIQ help. So it's filter adjacent matching lines. And then what is that? So count. Alright, so let's try it. UNIQ-C. Now what we're going to do is we're going to take the contents of this temp error.txt and we're going to feed it into that command as input into that command. So what we could do, we can say echo. Oh, yeah. So like instead of doing like echo hello world, you know, if you wanted to echo the contents of a file, you could do echo that and then like my file. I think unless that's an echo itself. Let's try it. Yeah, so like you can see here, this is actually interesting. Okay. Well, that's interesting. I don't get why it's not echoing anything. Maybe because they're standard error. So what if I put a 2 here? Or a 1 or a 0? Okay. Well, I'm confused about that, but that's okay. Let's just move on. The -C option makes UNIQ display how many times a repeated line appears in the text. As the numeric value of the redirected file descriptor was suppressed, the example command is equivalent to UNIQ-C 0 less than /temp /error.txt. To use a file descriptor other than 0 in an input redirect only makes sense in specific contexts, because it is possible for a program to ask for data at file descriptors 3, 4, etc. Indeed, programs can use any integer above 2 as the new file descriptors for data input/output. For example, the following C code reads data from file descriptor 3 and just replicates it to file descriptor 4. File descriptors, that's interesting. What is a file descriptor? This is the first time they've mentioned file descriptors. File. Oh, no, it's not. It was the first thing mentioned. So a file descriptor. So let's see here. You know what? I think I need to chat with the AI. So I'm going to ask it, what is a file descriptor? And a file descriptor is a unique identifier used by operating systems to manage and interact with open files, network sockets, or other input-output resources. It's essentially an integer value that points to a specific entry in the operating system's file table or input-output table. This entry contains information about the opened resource, such as its type, current position, access mode, or other relevant data. Okay, so let me ask you this. What are some Linux commands that are relevant to file descriptors. Okay, so open and close, of course, that kind of makes sense. Redirections, pipes, standard input, output, error, which we learned about here. LSOF, that's a good one. So LSOF will probably list file descriptors. I don't know what is a file descriptor a number? I'll ask it that. Okay, strace. Yeah, strace is a good one too. I remember. I don't know. Was it in this one where I learned about strace? I learned about strace at some point. So yeah, it's a number. Oh, okay. So, this is important. This is the missing piece of the puzzle. So, file descriptors start from 0 and increase sequentially as files or resources are opened. So there's some reserved file descriptors. File descriptor 0 for the standard input, 1 for the standard output, and then 2 for the standard error. But then beyond that, 3, 4, beyond, those are open file descriptors that can be used for other files. So like when they talk about file descriptor, so when they talk about file descriptor 3 and file descriptor 4, these are just actual files. So so the -C option makes unique display how many times a repeated line appears in the text as the numeric value of the redirected file descriptor was suppressed. For example, the example command is equivalent to uniq-c. There we go. To use a file descriptor other than 0 in an input redirect only makes sense in specific context because it is possible for a program to ask for data at file descriptors that are not the reserved ones. So like, you can access a file, without giving it the file name. You can just give it the file descriptor associated with it. So indeed, programs can use any integer above 2 as new file descriptors for data input/output. For example, the following C code reads data from file descriptor 3 and just replicates it to file descriptor 4. So file descriptors are probably pretty useful because like if you don't know if the name of the file is going to change or like the working directory of the file is going to change, just use the file descriptor. Like in my mind, that's how it works. Hopefully that is actually the case. All right, so note, the program must handle such file descriptors correctly. Otherwise, it could attempt an invalid read or write operation and crash. So this is C code. You know what, let's do this. But I'm not going to type it all out. I'm just going to paste it in. So the file name for this will be fd.c. fd standing for file descriptor, I would assume. All right, so set paste I. There we go. Sounds good to me. So to test it, save the sample code as fd.c and compile it. Using this command, gcc-o fd fd.c. Now, why do I need this fd there? Let's take a look at the help. We'll take a look at -o. So -o is, okay, so we're going to make a new file named fd. All right, so gcc-o, after it's compiled, it will be called fd. And then the file we want to compile is the source code of our C program, which is has the file name sd.c. All right. This program needs file descriptors 3 and 4 to be available so that it can read and write to them. As an example, the previously created file /temp/error.txt can be used as the source for file descriptor 3, and the file descriptor 4 can be redirected to standard out. All right, so now we're executing that program. I'm surprised you don't have to change the permissions to make it executable, but it looks like it should be fine the way it is. And then what we're doing is we're using this as the source for file descriptor 3, and then file descriptor 4 can be redirected to standard out. So I guess I'll just try this and see if it works. I don't really understand what's going on here, but okay, yeah, it looks like we got the same result that we had before. I issued it an additional time, so we have an additional error message in there. From a programmer's perspective, using file descriptors avoids having to deal with option parsing and file system paths. The same file descriptor can even be used as input and output. In this case, the file descriptor is defined in the command line with both less than and greater than symbols, like 3 less than greater than /temp/error.txt. Okay, that's interesting. So let me read that again. From a programmer's perspective, using file descriptors avoids having to deal with option parsing and file system paths. The same file descriptor can even be used as input and output. Okay, and do that with a less than and a greater than sign together. All right, so let me get all the way through this last section, and then I'll cut it at the guided exercises. Yeah, we're at 46. That's a good time to cut it. So next section, here document and here string. Another way to redirect input involve, I think they mean involves, the here document and here string methods. The here document redirect allows to type multi-line text that will be used as the redirected content. 2 less than symbols indicate a here document. Okay, that's actually pretty useful. So I've actually wondered how to do this, because like, for example, if we do echo, say I want to write on multiple lines, please help, and then we'll say like this is line 1, and then we hit enter to do line 2, and then we've got that special character in there as well. So if instead I do echo, and then I guess you got to do EOF. Oh, because otherwise it never. Yeah, so line 1. Yeah, line 2. And then what, an exit or something, or Control C? Wait. Okay, I gotta read more about this. So okay, yep. Indicated here, so there we go. Oh, you know what? It's like on Cisco devices where you set up a banner and you have to create an end character to know like when you're done typing in the banner. That's how it works. So if I do echo, now I could do stop like that, and I could do line 1, line 2. It's the terminating character. It looks like it actually did not echo it, but because you should see it listed twice there. But that's what EOF is. It's just a series of characters to let it know that you are finished typing. If you don't include that, then what happens? Yep, you need to include a series of characters to let it know when you're done typing, or else there will be an error. All right, so let's type in the example they got. So it'll just count the words. This could be actually really useful, because like I find myself needing to do this like quite a bit, just to like count words. And like what I usually do is like an online tool But like this could potentially be faster. All right, so at the right of these two less than symbols is the ending term EOF. The insertion mode will finish as soon as a line containing only the ending term is entered. Any other term can be used as the ending term, but it is important to not put blank characters between the less than symbol and the ending term. In the example above, the 2 lines of text were sent to the standard in of WC-C command, which displays the characters count. As with input redirects for files, the standard in file descriptor 0 is assumed if the redirected file descriptor is suppressed. The here string method is much like the here document method, but for 1 line only. Oh, this is interesting. So you can do this. You can do this for 1 line only, which is kind of interesting because I thought, can you do it on multiple lines? No. Okay, you can't. Oh, that's okay. Because I mean, you can just do this, right? Oh, you can't, because this is to feed it a file. So basically, like when you do this, you're feeding this to it as the standard output file. Yeah. So you're feeding it to it as a file descriptor 0, I believe, which is the standard input. In this example, the string at the right of the 3 less than signs is sent to the standard input. Yep, I was right. Of WC-C. So normally that only takes files, but if you want to send it just a typed out string of characters or something you paste in without it belonging to a file, you can do that if you send it to the standard in file and then use the 3 less than signs to feed it into WC-C. So which counts the number of characters. Strings containing spaces must be inside quotes, otherwise only the first word will be used as the here string and the remaining ones will be passed as arguments to the command. All right, so now we've got some exercises. I'd love to just finish these up, but I've got more on my plate today that I'd like to do. So I think it makes sense to finish it up. I feel like these might be a bit involved. I don't know. They look kind of easy. But anyway, yep, I got to finish it up here. So that's it for this video. Thanks for watching, and see you in the next one.